of my life, I've wondered whether the cosmos has meaning and purpose. Not just the made-up meaning of human psychology, however well-intentioned, or the blind purpose of physical regularities, however the natural beauty, but transcendent meaning and ultimate purpose. It's one of the big questions, and one way to explore it is to probe cosmic origins. How things really begin often provides clues as to what things actually are. This is true of all things in the universe, but is it also true of the entire universe? Does it even make sense to inquire about the beginning of the universe? Meaning and purpose may hang in the balance. That's why I'm compelled to return regularly to seek cosmic origins. I'm Robert Lawrence Kuhn, and Closer to Truth is my journey. I seek scientists who seek cosmic origins. In pursuit, I go to the Rocky Mountains of Banff, Canada, for a conference of physicists and cosmologists organized by the Foundational Questions Institute, FQXI. Although these conferences, held every 2 years, deal with diverse topics such as time, information, multiple universes, always they include startling theories and new evidence about beginnings. I'm thrilled to start with the scientist who revolutionized thinking about the beginning of our universe, Alan Guth. Alan's big idea, which captivated me, was the theory of cosmic inflation. That the very early universe went through colossal exponential expansion in a fraction of its first second. How has cosmic inflation been holding up? What progress has been made?
Alan, we're here at the FQXI conference, and I think this is our 5th time together, maybe over 13, 14 years. What's been happening recently with all the observational evidence in terms of inflation?
The observational evidence for inflation has just been mounting up, and as things get measured more and more precisely, it just gets better and better. So, for example, one of the predictions that inflation makes is for the average mass density of the universe. And now that's been confirmed to an accuracy level of about 0.5%. Wow. It's exactly what inflation predicts. One of the other important predictions inflation makes is for the patterns of the ripples that are seen in the cosmic microwave background radiation. And the most recent complete test of those fluctuations is from the Planck satellite, and the main result of the experiment was powerful evidence for the simplest models of inflation.
What is the prediction, and how does inflation predict a pattern?
In inflationary models, these fluctuations are attributed to quantum fluctuations that happen initially at the beginning of inflation on incredibly small size scales, where quantum effects are expected to be significant and are. And then inflation stretches these out to become macroscopic and visible in the microwave background. Because the pattern is determined by quantum physics, we can predict what that pattern is.
Yeah, that's really amazing. How about your own theoretical thinking over the last few years?
Well, one of the key mysteries still about inflation, really, is how we handle the fact that almost all versions of inflation have the property that once they start, they never completely stop. We call it eternal inflation. It's really future eternal inflation. It goes on forever, producing what we call pocket universes. And the difficulty with that is how to define probabilities, because everything that's allowed by the laws of physics will happen an infinite number of times in this multiverse. So it's very hard to know what you're talking about when you say that something is more common than something else. So people have been wrestling with that, and it's still pretty much an open problem, but we have a number of different proposals for how to extract finite numbers from the infinities. We don't even know what the right recipe is, but the recipes that give sensible answers seem to all have the property that they prefer small amounts of inflation rather than huge amounts of inflation. While in the old days, we used to think that huge amounts of inflation looked much more plausible.
So what's the implication of that?
One is that if you have a huge amount of inflation, it drives the universe completely to flatness, critical mass density. But if you have just minimal amount of inflation, then there's still a chance that we're not quite at the critical density and that we might measure a deviation from the critical density. So that now becomes a much more interesting thing to look for. The other important implication of minimal inflation is it means that our pocket universe is probably not as big as we once thought it was. In the, quote, old days, we used to think that our pocket universe was tens of orders of magnitude larger than what we currently observe.
You know, what happened before? How did inflation start?
Well, we still certainly don't know the answer to that question, and inflation, in fact, makes it a particularly difficult question to answer, because the gigantic expansion associated with inflation, really from an observational point of view, essentially completely erases any evidence of what came before. So thinking about what came before is pretty much entirely a theoretical issue.
What are some of the options? What are some of the differences that people are talking about?
One possibility that people have thought a lot about is the idea of a quantum origin of the universe, that's tunneling from something or not, some version of nothing, and there are different versions of nothing. But yeah, the idea is that somehow quantum physics can start with a state of nothingness and tunnel to a small universe, which then undergoes inflation. And there are different versions of that.
Allen's theory of cosmic inflation makes astonishing claims. Inflation transforms the smallest possible events, quantum fluctuations far smaller than an atom, into the largest existing structures, galaxies and clusters of galaxies. And once begun, cosmic inflation cannot end, so that an inconceivably large number of universes continue to be generated, perhaps an infinite number of universes. Among cosmologists, eternal cosmic inflation has become conventional wisdom. But even as observational evidence has been building support, not everyone is convinced, and I need to know why. I meet theoretical physicist Andreas Albrecht.
Andreas, most cosmologists believe that the theory of inflation is an accurate way to describe the beginning of the universe. And the general implications of that are two things. One is that our own universe is orders of magnitude, maybe exponentially bigger than what we currently see. And secondly, that the implications of math is that if inflation starts, it doesn't stop, so that there'll be maybe infinite numbers of other universes. So you agree with the inflation, but you question some of the conventional implications.
I do. If you believe in a little bit of inflation, it's very easy to conclude there must be a lot. But then it leads to some really weird stuff. I mean, inflation is advertised as a solution to tuning problems, where the universe itself looks delicately balanced at the beginning of the Big Bang. I think some people kid themselves this eternal inflating picture is free of those problems, but I think it is. And that's forced me to consider something other than the simple extrapolation back that you might naively do with an inflation theory. And one of the things that's actually motivated that is the dark energy and the possibility that we're surrounded by a horizon not much bigger than what we see today, that could really be the edge of the universe, not just the edge of what we see, but the edge.
I mean, that's really a minority position. Why are we able to see the edge of the universe? That seems unduly coincidental.
Well, there's a lot of talk about these coincidences. People wonder, why is the value of the cosmological constant, the dark energy, it is? Yeah. That's where that coincidence comes from. It's nothing other than that. It's not a new coincidence. But what I've done is take the quantum theory, suppose the quantum theory of the cosmological constant is different than what we've assumed, and where it really does close off and give us a finite universe.
But some would say that a finite universe is very strange because it's like an arbitrary number as opposed to infinite, which is normal or zero.
To me, infinity doesn't mean anything at all, because in science, we'll only ever have a finite amount of data. We'll only ever do science for a finite amount of time. So whatever data we have, there will always be a finite theory to match it. Oh, you'll never need infinity.
But that's an epistemological, a knowledge limitation. It's not an ontological or what's real limitation.
But I think we should respect that.
But in your view of a finite universe only 20% larger than what we see, it just seems so oddly coincidental with what we see. It makes us more special than we're supposed to be under normal scientific ways of thinking.
Well, people wrestle with these specialness questions. It's already a problem that people think about regarding the cosmological constant and the value. Why do we live at a time when it's coming to dominate the universe? Right. In my theory, right, it's the exact same puzzle. It's not that we've solved it, but it's not an extra puzzle.
I just don't understand that technically. Why is the cosmological constant, which describes the rate of expansion of the universe, with the size of the universe being what we are, why are those two related?
If it's a cosmological constant, our future is something called a de Sitter space, where all there is the cosmological constant, nothing else. Everything else dilutes away. And that has an interesting feature called an event horizon, which many people know about because black holes also have them. And one thing that's interesting about black holes is that if you're standing outside a black hole and you throw something in, you'll never see it cross the event horizon. Yeah. The way general relativity works is all you see is it approaching the event horizon. It takes forever just to approach it. And people have used that fact to consider a quantum theory of a black hole where, from the point of view of an observer sitting outside, there really is no inside. The event horizon is the edge of physics from the point of view of that observer. Now, I've just imported that concept to the de Sitter space. So I say the event horizon in that space, which surrounds us, is the edge as well. And there's no physics outside of it. So it's the presence of the cosmological constant that makes it possible to have this horizon. And the size of the horizon is dictated by the value of the cosmological constant.
An edge to the universe near what we can see, wildly coincidental, I'd say. But then again, that's how breakthroughs happen. Serious scientists challenging conventional wisdom. What's more, black hole horizons work similarly. So who am I to tell deep reality what makes sense? I cannot avoid cosmic coincidences. Could they hint at meaning and purpose? I'm suspicious. What could be behind such breathtaking coincidences? One approach is to assess the initial conditions of our universe. To produce our kind of universe, how would it need to start? I hear that Laura Mersini-Houghton, a theoretical physicist and cosmologist, has a theory. Coincidentally, she's here, attending the FQXI conference. I go find her.
Laura, what can you say about the confidence level that you and your colleagues have about how this universe began?
When it comes to the confidence level, that's still very low. We can see observationally up to the first fraction of a second in our universe's existence. So up to that level, we have total confidence that we understand our universe, we know what happened. The big question is, where did that come from? What gave the energy of cosmic inflation? Was there anything before? Can we even ask the question of what was there before? And that brings about a lot of deep questions, not just about our universe, but about nature itself, because to have the right to ask the question what was there before, we have to accept that there is such a thing as time. The very word before does not have any meaning outside of the context of time. So is time emergent or is time fundamental? That's one other question related to the issue of the origins of the universe. When it comes to that origin, to that first moment of our universe's existence, we are willing to accept that we can study it by quantum theory. The reason being that the universe was tiny. It was one of the smallest objects one can imagine. So it makes sense to accept that that structure can be studied with quantum theoretical rules.
So right now, what is the feeling that the universe was in its the smallest it was, many orders of magnitude smaller than the smallest particle that exists?
So it's a Planck
scale. So what was it at that time?
At that time, we can think of the universe as a wave packet using the wave-particle duality. It's equivalently, we can also think of it as a quantum particle. But that tiny universe had a very high concentration of energy, and it was that energy that drove it into an explosion. The question becomes, but where did that energy come from? Why did we have to start that way? Sir Roger Penrose calculated that the probability to start with high energy inflation is ridiculously small. It's 10 to the power 123 times. So 10 to the power 10 and then another 123 zeros. But so that says that the chance of our universe starting the way it is seems ridiculously small, nearly zero. And that brings about a lot of paradoxes. So that makes scientists feel very uncomfortable, because it seems to indicate that something very special produced the initial conditions for our universe to come into being. On the other hand, it's hard to see how can we even ask the question, why did we start with this universe, without having a pool of many possible universes from which to start, from many possible initial conditions. We all agree there's nothing wrong with applying quantum mechanics at the beginning of the universe, because the universe is so small. If you apply quantum mechanics, what you find out is not just one solution, one wave function that will eventually become a universe, but a whole family of them. And there is no criteria in nature that says, oh no, you can keep only this one. So if you agree and accept that all the possible mathematical solutions one gets out of quantum mechanics have an existence or a right to exist similar to our universe, then we have to accept that there is a whole pool, ensemble of universes out there that underwent a similar evolution to ours. Starting from that wave packet initial state.
Laura goes from the extraordinarily unlikely initial conditions of the universe to the existence of multiple universes. A logical move that seems almost required unless one wanders or stumbles into supernatural territory. Me, I refuse an easy pass by invoking non-physical explanations, but I'm not adverse to taking a closer look. Others seek supernatural explanations actively, regularly, religiously. They argue from the same set of extraordinarily unlikely initial conditions, but they get to God, or something like God. I speak with a quantum physicist who, to the amazement of colleagues, believes seriously in God, Don Page.
Now, as an evangelical Christian, I would believe that God did create the whole universe, and I don't believe he just created the beginning and then let it run, but I do believe that he uses very elegant laws for creating the whole thing.
What do you mean by the whole thing? You mean the whole
history? Right, the entire block of
four-dimensional time.
The four-dimensional block of the universe, and of course in the quantum theory, this would be sort of like a whole Everett multiverse, a block of many different histories.
So that's a lot of work to do that.
Yes, well, I mean, I believe God is infinite and he can do that, but he seems to use very elegant laws. Now, these laws are his own invention. God has chosen to use very simple patterns for creating the future time from the past time. I mean, we can't because we're too puny, but if there was some supernatural angel who could fully understand it, if God told this angel exactly what the initial state was and the laws he was going to use, then the angel from those should be able to deduce what God is doing for the rest of it. Now, that doesn't mean that God didn't have free choice in doing it. It just means that God chose to use those particular laws and that particular initial state to evolve the universe.
And that would become completely deterministic, even though it is this vast ensemble of probabilistic universes the way we look at it.
Yes, I think in my own view, there's not really randomness in quantum theory, except there is the uncertainty, of course, as to which branch we right now are on. It's sort of like the same uncertainty as to the uncertainty of why my present experience is seeing the universe from this direction and you're seeing it from that direction. I think both are real, and I guess I am one that strongly believes that God created the entire universe from nothing, and in my view, that means he had to totally determine it.
Now, many quantum physicists who do believe in God would say that God created quantum physics to allow a flexibility or an uncertainty to play in the universe so that human interactions, human free will can be built into the system.
Yeah, I mean, Einstein said that God does not play dice, and I tend to go even further and say that God could not play dice, if by playing dice I mean using something that gives random results that are not already determined by what God's doing. There's no random choices. There's nothing out there for God to bring in and use. This is all determined. But from our point of view, we can only see one outcome. So for us, the result looks random because we don't see the other parts. And God, if he had nothing other than himself to start with, I think that God doesn't even have the opportunity to be able to have randomness, that he had to create everything, and therefore I think he had to determine it all.
To Don, God not only created our universe, but also an unimaginably vast branching of total universe histories. I've not dreamt of the ideas Don makes me consider. To his credit, I like that. Never mind that I don't believe a word of that. When dealing with the origin of the universe, we must emancipate our minds, and Don helps me expand my thinking. I should come back to Earth, or at least back to our universe. With all my focus on how the universe began, I've neglected the prior, deeper question, if the universe began. I ask a quantum cosmologist, also attending the FQXI conference, who claims that our normal sense of beginnings or origins may not apply to the universe as a whole. James Hartle.
When people talk about the beginning, we have to ask, what does that mean? What is the beginning of the universe? If we assume that the geometry is classical, so we have a well-defined notion of time, you can talk about sequences of things in time, and you can try to extrapolate. This is what cosmology is about, the history of the universe backward in time.
Okay.
So how far can you go with that?
Right.
It depends on what you mean by what you think the limits are. If you're talking about the classical theory of general relativity, which is what we use in discussing the Big Bang, you can only go so far before the solutions, which represent the universe, develop singularities, infinities. And so what that really means is that the theory has broken down. Right. That is quite early, right? It's like 10 to the minus 43 seconds after the Big Bang. Yeah. And that's what most people are talking about when they talk about the beginning. Very early, back to the limit in which we can meaningfully describe a notion of time.
So that's way before inflation is supposed to be.
Way before inflation. Yeah. A lot of stuff works,
yeah.
Right? Starting with very simple initial conditions, we can have a whole story about how the universe. So the question is, can you go further? Well, if you go further, you're in the realm of quantum mechanics, not certain space-time, but probability amplitudes for space-time. Then it depends on what the theory are. For example, you could make a quantum transition to a different space-time on the other side of this region where the classical physics doesn't apply. So you can go through quantum mechanically.
Sort of like magic.
It's a very simple thing. If you think of the decay of an atomic nucleus, it's sort of like bound inside the nucleus and it's bouncing around. Yeah. There's a sense in which you can describe classically what's going on inside the nucleus. But to get out, it has to tunnel through a barrier because it's confined by the nuclear forces. But it can tunnel quantum mechanically through the barrier and then behave classically on the other side. Mm. That's two regions of classicality connected by a quantum transition. Could the universe be like that? It could, right? Where we make a quantum transition to another universe on the other side.
So, but how does that help us understand what happened originally?
One possibility is there's another expansion on the other side.
So what would be the implications of that? Eternal expansion?
So it would expand on both ends, right?
Right.
Unfortunately, what also reverses is the arrow of time, according to our calculations. Right. So the arrow of time would point the other way. Their direction of time is going towards the direction of expansion. To signal us, they'd have to go backward in their time. Not possible. So they're effectively disjoint. So classical description, back to a very early stage, possible quantum description, not much help in explaining the universe that we have.
And so what is the fundamental implication of the Hartle-Hawking state?
Well, the most useful application are the prediction of the features of the universe that we see today coming out of the state, because we get probabilities for those different classical histories. And that's how you test the theory of the quantum wave function of the universe against the observations. Not by having classical physics, but having an ensemble of possible classical universes.
To seek cosmic origins is an ancient and worthy yearning. No wonder it stars in all FQXI conferences. In the past, even if a final theory of how the universe began remained beyond us, the question itself always made sense. That is no longer clear. Perhaps there's no temporal boundary to the universe. Perhaps there's an infinite branching of total universe histories. Perhaps the universe is much smaller than we've come to think. What do we know with reasonable confidence? Cosmic inflation is a powerful theory with increasing support from cosmological measurements. The initial conditions of our universe were remarkably precise. What was the very first event that ever occurred? My hunch is that we're at least several breakthroughs away from a satisfying answer. My night musings drift from cosmic origins to ultimate origins. If the former is staggering, the latter is stupefying. I wonder whether science, as we conceive it, will ever be capable of discerning ultimate truth, far beyond, closer to truth.
For complete interviews and for further information, please visit closertotruth.com.